Hello there. In this session, we'll study motion under the influence of gravity. So we're going to talk about motion under gravity. Now we have already studied the three equations of kinematics, and you must be aware that acceleration due to gravity has a constant value. We take this value to be 9.8 meter per second square. But for most calculations, we prefer taking this value to be 10 meters per second square. And we denote this acceleration through the symbol small g. So small g represents acceleration due to gravity. Now this is the acceleration that any object close to the surface has when it is allowed to fall freely. So falling freely means the object is not acted upon by any other force. Right. So let's look at a simple example. Let's say a ball is dropped from a certain height h above the ground. So this is the height h from where an object has been released. Now when something is released, so releasing something, so whenever you see the word release, you should understand that the object was given zero initial speed. So that is the difference between releasing something and throwing something. So whenever something is thrown, you essentially give it some initial speed with which the particle moves. Whereas releasing something means that no initial speed has been given to the particle. Right. So here we see an object released from a height h, and we want to look at the subsequent motion. So when the particle is released, there is no other force acting on this particle other than gravity. And because of gravity, we know that there will be a constant acceleration given by 10 meters per second square. So the acceleration, which is acceleration due to gravity, has a constant value which is 10 meters per second square. And we know that as long as a particle has constant acceleration, the equations of motion are valid. So for the motion of this particle, we can write the second equation, S is equal to ut plus half at square. So now we are trying to modify this to fit our given condition, that is a particle falling through some height, right? So the displacement in this case can be replaced by h, right? Because whatever is the displacement will be the height of the particle. So the height covered can be written as 0 into t plus half into gt square. So this can be given as the height through which a particle falls after a time t when it is released from a certain height, right? So this was a first analysis of a simple situation. Now we'll look at some standard situations that you will encounter. For example, let's say that you are throwing this ball from the ground level. So you throw this up with an initial speed v0, and you are interested in finding, first of all, the maximum height. So let's denote this by capital H. So we are interested in finding out the maximum height that is attained by this particle. And then we are also interested in finding out the time after which the particle lands back on the ground. Now let's start by thinking why there will be some maximum height. You know that this particle has a constant acceleration which is downwards, having magnitude 10 meters per second square. So we are going to use the general symbol g, right? So the particle has an initial speed upwards, the acceleration is downwards. So after some point, its speed is going to reduce to 0, right? So when the speed reduces to 0, that will be the maximum height attained, and after that the particle will start to fall again. So particle first rises up to this height and then starts to fall again. So we see that the condition for h max, so at h max the final speed becomes 0, right? So we can use the third equation of motion, and the reason we are using the third equation is because we know the initial speed, the final speed, the displacement we are interested in, and the acceleration is known to us, right? So we use the third equation of motion, which tells us that v square is equal to u square plus 2as, right? So once again, when we talk about gravity, the acceleration first of all will be g. Secondly, notice that this equation, acceleration and displacement, are vectors, right? So you have to substitute them with suitable signs. Now, whenever we analyze the situation involving gravity, you can keep a standard notation where you take upwards as positive. So upwards direction will be positive, and therefore the downward direction will be taken as negative, right? So now think about acceleration due to gravity. Acceleration due to gravity acts downwards, right? Therefore, the symbol, the vector form of this acceleration will be minus g, right? So the negative sign comes from the fact that this acceleration is downwards. So now substituting this value, we first of all get 2 into minus g. Now displacement, you see the particle was initially at the lowermost position and now it is at some height, right? So the displacement is upwards and we have taken the magnitude to be h, so the displacement is plus h. Now as for initial speed, since this term is a square, so we can not worry about the sign as much, but you should still always try to see vectors for their direction, right? Now the initial speed was v naught, so this term becomes v naught square. Also notice that since we are talking about h max, we said that at h max we'll have zero final speed. So this height is h max and correspondingly the final speed is 0. So you get that v naught square is equal to 2 into g into h max, which gives you your final result that h max is equal to v naught square by 2g. So this gives you the maximum height which will be attained by this particle before it starts to come back. Now, there's the second term which is coming back. So whenever you see this term that something has come back, you should immediately interpret that coming back implies that displacement is 0, right? Because if you start from a position, you move for a certain time and then come back to the initial position, you know that your net displacement is going to be 0, right? So when we talk about the time to return, if I call this time t naught, then at t equal to t naught, we know displacement will be 0. Now think about which equation you know where displacement and time are a factor. Clearly, it is the second equation, right? In the second equation, if I write this down, s is equal to ut plus half at square. We know the value of time. We are supposing it as a variable. The s is known to be 0 and a we know has a fixed value which is minus g, right? So substituting these values, we see that 0, because at t equal to t naught, displacement is 0. 0 is equal to v naught into t naught, because when displacement is 0, time is t naught, plus half into minus g into t naught square, right? Now the calculation is fairly simple. You see that one of the t naughts can be taken as common. So you have half into g into t naught equal to v naught. So you finally get t naught is equal to 2 v naught by g, and this is the time after which the ball returns to its initial position. So these are the two standard results that we will use time and again when dealing with motion under gravity. Now, that is it for this session. In the next session, we'll look at some more interesting results and we will solve some problems based on these concepts. Thank you. Hello again. Before we move on to see some more applications of motion under gravity, let's try to visualize this motion. And what we are also going to do is see how, if a similar motion happens in two dimension, what are the similarities? Now, this will give us some interesting insights, which will certainly help us when we go on to study two-dimensional motion and look at projectiles. So let's start with one-dimensional motion, which is our motion of a particle being thrown from the ground, reaching maximum height and then coming back, right? So you see how initially it is thrown with its initial speed v naught. You can see it slowing down and now it reaches its maximum height. Here it stops momentarily, right? Understand that it will not be at zero speed for very long. It will be at zero speed for just a moment and immediately it starts to fall down. Also, if I look at any given height at any general point, the speed it had while going up will be equal to the speed while it comes down and reaches that point, right? The only difference is that while going up, the speed pointed upwards, and while coming down, the speed pointed downwards, and hence you can say the velocity changed its sign, but the magnitude remained the same, right? So we found out the particle went from ground, went to a maximum height, we estimated this height, and then it finally comes back. We also found out the time for such a motion, right? Now let's think about how this will translate to a two-dimensional motion. Now in two-dimensional motion, a particle is thrown at an angle with the ground. It goes on to reach a maximum height once again, right? It reaches a maximum height and then it falls back to the ground. Now, you are well familiar with vectors and you also know how to break a vector down into two components. So here you see when the particle is thrown, it has x and y component, right? So think about what will happen when it reaches the topmost point. So when it reaches the topmost point, the x component of velocity will not be lost because there is no force in the x direction. So at the highest point, once again, the speed will be zero, but only the y component will become zero, right? Because x component will never change. Also, so this is one of the things that we will use to find out maximum height attained when we go on to solve these problems. The second thing we had found out in this one-dimensional case was the time of flight, the time after which the particle falls back. So in this particular case, once again, you see the particle goes on to fall back to the ground. So what do you think can be the condition for when the particle falls back to the ground? You may have guessed it. Once again, if you think in terms of vector, so there is some displacement in x and this entire displacement is called the range of the projectile. So we'll study these things in detail. So this x displacement is the range, but what about the y displacement? So once again, when the particle falls back, it implies that y displacement, the displacement in the y direction is zero. Right, so I hope this helped you visualize the situation and also helped you compare how 1D motion is not very different from what is coming next, which is two-dimensional motion. So that is it for now. Let's get back to some calculations.